Okay, so let's see. Okay, any questions, comments? No? See if I can find the slides that I want to share. Okay, let me share the screen. So we were talking about the covariance matrices. Let me remind you. Oh, sorry. For some reason, it stopped working. Share again. Okay. So you see my screen, right? So yes.
Yeah, we can see it.
Okay, good. So we started talking about the covariance matrix and covariance matrices. And what we have here is, yes, so this is the definition. And just to remind you, there is a covariance between any two pairs of random variables, right? And this covariance is a scalar, and we can extend the idea to a vector, a random vector, where we have, let's say, n coordinates. So we have these pairwise covariances between a pair of random variables. And we have, let's say, many of those pairs. And you can arrange them in a matrix we discussed like this. So you get the variances on the diagonal, which are the covariances of the coordinate itself. And we also get the sometimes called cross covariances on the off-diagonal elements. Okay, and so we talked a little bit about the properties of this. So we have a matrix. So covariance. So the notation is I sometimes write something like that for a vector. This is a little bit different than a notation like this. So covariance of a random variable with something else has two, or takes two inputs. Whereas the covariance operator with some abuse of notation can be used for a vector. This outputs a matrix whose entries are these pairwise covariances. I hope this doesn't lead to too much confusion. We talked a little bit about this slide, which I hope everyone went through and took a look at this. And this is some of the interesting properties of a covariance matrix. So a covariance matrix is symmetric. Sigma is equal to sigma transpose. If the vector, the elements are pairwise uncorrelated, then the covariance matrix will be diagonal. This is also from definition, clear from definition. And if I let mu be the expectation of y, I can have these nice expressions, either this or that, for the covariance matrix, which is the matrix version of this scalar identity. So instead of computing this pairwise, I can just compute the whole matrix in one go by forming this, what I call y tilde here, the centered vector y, and multiplying it with the transpose of that matrix. Okay, and what we have now is, so this simple expression, which is covariance of y is expectation of y tilde transpose. This is useful in some, let's say, derivations. And then we have this last result, which is if I rescale a vector by alpha, the effect on the covariance matrix is that the covariance matrix is multiplied by alpha squared. And if I shift the covariance would be, I'll have the covariance be invariant to, the covariance will be invariant to that shift. Okay, so this is a recap of where we left last time. Any questions, comments about these ideas? Is it clear to everyone? This is all good? Okay, so let me ask you, did anyone get a chance to look at the video lecture going over lemma tree and the proof? Let's say how many of you have gone through this? No one? You can raise your hand. Interesting. So no one looked at the lemma tree? 1%? I guess that's the price of making it optional. Okay. So Jonathan, do you want to maybe say what was your impression? Did it work? Like, did you understood everything?
Yeah, I mean, I understand how it works. I just doing it myself would take a little bit longer just because I would have to look over all the properties that was discussed in the previous slide.
But you managed to prove that you managed to prove this yourself? Is that what you're saying?
And I was saying if it was like a homework assignment.
Oh, okay. You could prove it, right?
Yeah, it would just take a little longer than the 10 minutes that you went over the proof.
Okay. So anyone else did this exercise? That's great. It's okay. I mean, you get better at by doing it more. No one else went through the proof? So maybe, do you want to help us? Maybe I can briefly go over the proof. Do you mind if you? So the idea is that this is an extension of the result that we had for the expectation. So I have a random matrix Y, and I want to compute the covariance of A times Y, where A is a matrix. And this is not as straightforward as the expectation, where you just pull A out, because this is something second order. You would expect to get a square of A out, just like this, where we get alpha squared out for a scalar. But A is a matrix, so things become a little bit more complicated in the sense that you get A squared, but the A's appear on the different sides of the covariance, and you get A and A transpose. So this is an example where things might not be as obvious as they seem. So do you want to help going over the proof? No? So what I'm going to do is that I'm not going to go over the proof then. So you can go over the proof in the, I have a detailed explanation in the recorded lectures, and I also encourage you to go try to prove it like Jonathan did for yourself before looking at the lecture notes. So all you need are these properties that I listed, or in fact, what you need is this, and the lemma we had for the expectation. So if you have this lemma and you have this definition, you should be able to prove this result. So I'll let you prove it for yourself. And there's an example that I'll let you go over it for yourself. I'm going to give another example. I'm going to do a different example. This is also another example which you can go over. I would like to give a different example so that it complements. So maybe I should do it here. Let's try this. Sorry, let me try to see if I can. move this guy. Oh, I can't move it. This is stuck. So let me try. So I have to do it at the end. Move to another page. So let's say I have, let's say x1 and x2 random variables. And let's say I have z1, which is x1 minus x2, and I have z2, which is 2x1 plus 3x2, right? And then I want to compute the covariance matrix of z1, z2. I would need some information to be able to compute this. Anyone knows what kind of information I would need to know about x1 and x2?
If they're independent?
Yeah, that would help, but I need less than independence. I need something about their joint distribution, but independence is too, let's say I say that they're not independent. Is that enough? So x1 and x2 are not independent. So this matrix is covariance of, so if you recall what I mentioned, this is going to be variance of z1, covariance of z1, z2, covariance of z2, z1, and then the variance of z2. So what do we need to be able to compute these?
Do we need variance of x1 and x2 and covariance of x1, x2?
Yes, so we need variance of x1, variance of x2, and then the covariance of x1 and x2. In fact, these are the only things that we need. So these two being not independent implies that the covariance is non-zero, but doesn't give us much information. So let's say I'm going to assume the covariance of x1 is 1, covariance of x2 is 1, and this is, let's say, anyone knows what the range of this could be? If I want to construct the covariance, can it be, let's say, 2? Do you guys remember the correlation coefficient ideas? Can it be 10?
Isn't it like 1 where less than the correlation times, it's equal to correlation times the standard deviation of x1 and standard deviation x2? So
Yeah, so the correlation coefficient, yeah, correlation coefficient is the covariance. This is like this, so less than the root of the variances. And you should have seen that the correlation coefficient, the absolute value is less than or equal to 1. So from these ideas, it means that the covariance of x1, x2 should be an absolute value less than the root of the variances, the product of the variance. So this can't happen. So the range that is valid should be between -1 and 1. So let's say I make this 2. Actually, let me do it. So this is 1. I'll make it this be 4. Then the covariance can be at most 2. So I can assume it to be, let's say, -1. Okay, so the absolute value should be between -1 and 1. So this is good to remember. There is an upper bound on the covariance, absolute value of the covariance. Okay, so this is a valid data for this. So I have that. So this is a psi. Is this clear? So psi. There is some relation between the covariances and variances. So you can have It just helps if you remember that the correlation coefficient has to be less than or equal to 1. Yeah, so that. Okay, so my data now is this. So how do we compute this? There are multiple ways. I want to hear your thoughts. Maybe think a little bit about this. Say 30 seconds, maybe. Okay, any ideas how to proceed?
We just kind of plug it in with variance that started with each one, like variance of Z1 equals to variance of, I think it's X1, sorry. Do you mind going up a little bit, Professor?
Yeah.
Yeah, sorry, variance of X1 minus X2. And we'll just use the property to, this is equals to variance of X1 plus variance of X2.
Okay.
Okay, and this is equal to 5.
Okay.
Just 1 plus 4 equal to 5.
Okay. So 1 plus 4 equal 5. So is this okay with people? So let's stop here. Is this, everyone happy with this calculation?
Yeah.
Yeah. Any other? Everyone okay? So how can I say that this is not okay? So let's say this is not okay. Anyone now wants to? This is the first thing that you would do. And it would be okay if X1 and X2 were uncorrelated, but you have a non-negative correlation.
Oh, yeah, my bad.
Yeah.
That's, yeah, I totally messed up. So we have to do the plus 2AB covariance X1, X2. Thanks for catching that. So it's minus 2 covariance of X1, X2.
Okay, so this is good. Now, we can compute this, but just to remind you what this is, we can drive this. By definition, this is like this. So you don't necessarily need to remember formulas. So covariance is bilinear. Do you remember this term? Bilinear. It came up before. What else was bilinear?
Inner product? Inner
Inner product,
it was last time.
Yes. Inner product is bilinear. And I'm telling you that the covariance is also a bilinear operator. So what does that mean?
Does that mean that we can separate each term into like covariance of X1 minus covariance of X1, X2?
Yes, right? Exactly. Yeah, so it's like you can treat this as if you're multiplying these two terms. The way that you distribute these, like X1 times X1 minus X1 times X2, as if we are expanding this. Minus X2, X1 plus X2, X2. So covariance of x1 minus covariance of x1 x2, right? Minus covariance of x2 x1, and then this times that, the signs get plus, so plus covariance of x2 x2. Okay, so this is the variance of x1. This is the variance of x2. And these two, how about these two? Can I simplify? Covariance x1 x2, covariance x2 x1.
Would it just be the -2 covariance of x1 x2? So we can flip them, the x2s and the
Yes.
x1s.
The covariance is symmetric, so you can say negative two times one of them. So you can see this is giving you back the original formula that you had. Okay, so there's no need necessarily to remember. After a while, you remember this is like as if you're squaring, right? This is like squaring this. So the formula would be similar. So this would give me 1, and then this is 4. This is going to be +2. So we get 7. So the result would be, if I haven't made a mistake, this is going to be 7. Okay, is this clear to people? This operation?
Yeah, it's clear. And that's just a property of covariance being bilinear.
Yes, that's a property of the covariance. So that's the property of this covariance operator that acts on two random variables. Okay. If you want to apply it to this matrix version, we didn't have the matrix version for two arguments, but can actually do it that way as well. But once you understand this for two scalar random variables, then you can do it if these two were random vectors. The meaning would be cross covariance matrix, which we didn't talk about, but it's easy to understand. Yeah, but that's a property of covariance, and you can prove it to prove so bilinearity of covariance operator. In order to do this, so you have to say that I have a bunch of random variables like sigma I from 1 to, and let's say AI, xi, and then I'll take the covariance with j from 1 to m, bj, yj. These are linear combinations of two sets of random variables. I can get this as j from 1 to m, ai, bj, covariance of xi, yj. So that's what bilinearity means, effectively. And you can prove this using the definition. So as an exercise, if you're really interested, prove as an exercise. Okay, it could be good for you. This is one of the important properties. So now you know two operators that are bilinear. One is inner product, and one is the covariance operator. And I can add 1/3 piece of information which we don't use, and you can actually use covariance to define inner products between two random variables because it shares the same properties, or it shares the desired properties to inner products. But that's like an aside. So you could think of random variables as vectors in some space, and then define angles between them by taking the covariances. But that's like an advanced topic. In any case, so this is a very important property. Any other question about bilinearity here? Okay, so I guess we calculated this guy. We can as easily calculate this. So if you have, let me copy this down there. So that's our setup. So I can calculate covariance of Z1 and Z2. Anyone wants to use bilinearity to help me with this?
I just have a quick question about this, like the covariance matrix.
Yeah.
So, if we're trying to find a covariance matrix, like for example, in the homework where it's like more than 2 by 2, will we just use definition 1 and just like plug in the each of the ij's? Definition.
I'm not sure if I understood. So what do you want to compute?
So like, for example, in homework 1, we have like, so we define like new variables, y1 equals z1 plus 2z3, y2 equals z1 plus z2 minus z3, and then y3 equals 2z1 plus z2 plus z3 minus 7.
Sorry, let me see if I can pull up the homework. Homework
Yeah.
1. Okay, let's see. If I share my screen, I think, so that everyone can see. Can I see if I can share it? I might have to drop. Just give me a second, see if I can find the way. Share. Okay, so do you see the homework problem?
Yeah.
Okay.
I was talking about question 3.12. So yeah.
Okay.
So will we just use like definition 1 to kind of like fill in for the covariance matrix of y?
So the example that I'm doing here is similar. So
Okay.
what I'm trying to do is there are multiple ways that you can do.
Mhm.
So this is similar. So for example, what we're doing here is, so here instead of y, so this is y's in terms of z's, I have like z's in terms of x's,
Okay.
right? So you can go ahead and do the thing that I'm doing now, which is take the covariance of y1 and y2, and the covariance of y1 and y3, and then fill out from that definition, fill out the entries, just like this, right? There's another way, which is using lemma tree, which I'm trying to also build. So we can use this lemma tree as well,
Okay.
which I want to use. But let's try this. Yeah, let's first try our standard approach. This is the basic approach that you should know, and you can apply it to that problem. It's very similar to this, but let's work out this, and then you can figure out that one as well. So if I want to do the covariance of Z1 and Z2, how can I proceed? It's going to be covariance of x1 minus x2, 2x1 plus 3x2, right?
I think
Professor?
you're still sharing the homework screen. Yeah.
Okay. Sorry. See if it worked. No, it did not work. Okay, let's hope it works this time. Okay, works now, right? So I want to compute this covariance, Z1 and Z2. I just plugged in Z1 and Z2. So how do you do this?
Would you just separate them one by one? Go from 2 of variance of x1, because we have covariance x1, x1.
Yes.
And we can
This
do
times
a
this.
minus 2 covariance of x1, x2.
Minus
plus 3.
2, yeah, it's like, yeah, covariance, so let's say x2, x1, it doesn't matter, but that's the same.
X1.
Yeah, that's these.
Plus 3.
Covariance, so x plus
3 covariance of x1, x3, x2.
Which term are you looking at? This and
x1 and x2, the first term and the last term, yeah.
Yeah, covariance of x1 and x2. And
minus 3 variance of x2.
Covariance of x2, which is these two terms, right? So this term and that term, right? So you just expand as if you're multiplying the two, like polynomials, basically. So let's check. So it's this times this, which is 2 times variance x1. The first times, the second from the first coordinate times this first term. The second coordinate is the second one. X1, x2. Yeah, this looks good to me. Does it look good to everyone? This is as if we multiply the two. Looks good. So this would be 1 by assumption. This would be 4. This would be -1. So the sum of the two is like, so I can also combine these two, right? So these two are the same. So I can get 1 times covariance of the pairwise covariances. So maybe I should write that separately. So you get 2 times the variance of x1 plus covariance of x1, x2 minus 3 variance of x2. And so this is 4, this is -1, and this is 1, right, by assumption. So what do we get? We get 4, right? So how about the other one, variance of z2? Maybe someone else wants to also.
Wait, Professor?
Yeah.
So the answer we got is 4. Shouldn't it be?
Oh, right. You're right. What should it be? Seems like negative something, right?
-11?
-11, right? Twice this minus, right? Great, thank you. Hopefully correct. Okay, thanks. So now someone wants to go with. Should I call on someone?
Yeah, Professor, there's a game that we used to play in orgs for like popcorn. So you can just let someone else call someone. So
yes, that would be great.
Like,
yeah, that would be, the guilt would be on the person that, yeah, I'll be like blameless. So maybe you should call on someone.
Popcorn someone? Okay. I want to popcorn Max. Hey Max, how you doing?
What's up, Danny? Okay. So do you want me to solve out variance of 2x1 plus 3x2?
Yeah.
Is that what we're doing here?
Yes.
So it would be 4 times the variance of x1 plus 9 times the variance of x2 plus 12 times the covariance of x1, x2.
Great. Okay. That's great. That's it. So everyone understands this? Well, people dropped out of the class because now they have to. Interesting. So you're now like 5%. So I have to figure out some way to encourage you to stay. Okay. So this is 1.
Don't worry, Professor, I'll stay.
I know, but I want more people to stay. Otherwise, okay. So -1, 4, 1. What is the result?
Would it be 28?
28, yeah. That's what I had to.
Okay, I'll believe you guys. So 28. Okay, so we've done the thing that we started to do. So covariance of Z1, Z2 is okay. where did we compute this? So 7, negative 11, 28. Okay. So how about doing it using the lemma tree now? So lemma tree says that covariance of the vector called this z can be written. Oh, if I can write z as a times, let's say, vector x, then I have that this is a covariance of x times a transpose. So can I write vector z as a matrix times x1, x2? So maybe think a little bit about that. Maybe Max, do you want to call on someone?
Yeah,
You can also
Jonathan, you
call
wanna
on
do that?
yourself.
No, I'm not going to call it myself. Jonathan, you want to handle that one?
Yeah, what am I doing?
So can we write this z1, z2 as a matrix times x1, x2?
Yeah, I believe so. Yeah, because we could just factor out that x1 and x2, couldn't we?
I have done it, but I need to fill in this matrix. So there would be a 4x4 matrix here. I want to I want to have these relations between x's and z's. So how can we do this? I'm going to help you out so I can
it's
do.
just 1, -1, 2, 3.
Yeah, okay, great. So if you multiply this out, you'd get the original system of equations. So this is our A, right? So now I have that A is A times, this is vector x, this is vector z, z is A times x. Now I can write this as covariance of z is equal to A covariance of x times A transpose. So what I would get is 1 minus 1, 2, 3. Covariance of x is 1 here, 4 here, -1, I guess. That's our data. Okay, so that's covariance of x. So that's the variance of x. That's the variance of x2, variance of x1, variance of x2, and this is the covariance. Right, I'm using this information that I have here. And then the transpose of this guy, which is 1, 3, and I just flip the off diagonal. So now I can multiply out, and hopefully I get this. So I'll let you do the math and see later for yourself whether this has to come out as 7, -11, -11, 28. Okay, so this formula just reduces the problem to a matrix multiplication. Okay, it might not be as easier as, or easier, it might not be easier or the easiest approach, but I just want to wanted you to see that there are other approaches, and this one also works. And we'll see. We usually want to use this formula from a theoretical perspective, so we might not be interested in exact calculation using this, although it's just the natural way to do it if you have the matrix A. So if you want to do it on a computer, this is the easiest probably, instead of going through this calculation one by one.
Professor?
Yeah.
Is there a correlation between how we're doing this to like spectral decomposition? Because this looks pretty similar.
That's a good question. You're talking about, for example, that if I write this as a matrix, let's say sigma, this looks like what we had in the spectral decomposition, which is U lambda U transpose, right? Is that the question, or?
Yeah, is there like correlation, like if x and y are if Z1, Z2 are, sorry, if X1, X2 are independent, then it's like also.
Yes. Yeah, so if X1 and X2 are independent, then they're uncorrelated. So independence is stronger than uncorrelated. So if X1 and X2 are independent, then it follows that they are uncorrelated. Then it follows that the covariance of X is diagonal, right? So you get variance of X1 and then the variance of X2 and the zeros here. So this middle guy would look like that, but A is not necessarily an orthogonal matrix. So you can verify, for example, this A is just not orthogonal. So if I multiply the columns, they're not orthogonal. And the columns do not normalize to 1. So there is, it looks similar, but it's not always, this is not always an orthogonal, like this is not an eigendecomposition of the covariance of Z. If it happens that A is an orthogonal matrix and sigma is diagonal, then yes, that would be the orthogonal decomposition. But this is, in general, not an orthogonal, sorry, not a spectral decomposition.
Okay, yeah, thank
Okay.
you. It just looks very interesting.
Yeah, so the formula looks like it, but there is a resemblance, but they're a little bit different. Okay, other questions? Does this make sense to people? So let me add one more piece here. So if I had Z1 is equal to X1 minus X2, Z2 is equal to 2X1 plus 3X2 plus 5, let's say. Could you tell me what difference does it make in the covariance matrix? I can write this as Z1, Z2 equal to 1 minus 1, 2, 3, X1, X2 plus 0, 5. So can we use a property of the covariance operator? I'm going to call this B. So we have Z is equal to A, X plus B, where B is constant, A is constant, X is random. So can I say something about the covariance of Z?
Yeah, wouldn't be the same.
Why?
Because the covariance or variance of a constant is 0, so it would be the same.
Yeah, or you could say it's a little bit tricky because you also have to take the cross covariance, but cross covariance would be also 0. So this is a special case of what I had written here, that if you shift the covariance matrix by a constant, it doesn't affect the covariance. So adding a constant to covariance matrix, as you pointed out, it's like adding a constant to a variance. It doesn't matter. You can say it's going to be the covariance of this, covariance matrix plus the covariance matrix of this, plus twice the cross covariance. Both the variance of B and the cross covariance are 0. But in any case, so this is related to that over problem that was asked. Okay, so any question about this? So you at least know two different ways of computing the covariance matrices, and you can go through these examples. These are exactly the same type of arguments. So I want to emphasize that this lemma is very important, and I encourage you to go through it to do the proof, and also go through the examples and make sure that you understand this. Okay. Okay. No questions about that? Yeah, that. Okay, I assume none of you have looked at the following. Have you looked at this proposition? Okay, so I'm just going to go over this. This is another property of the covariance matrices. So we talked about positive semi-definite matrices, if you recall. So anyone recalls what the positive semi-definite matrix was?
Isn't the case where if all the eigenvalues are greater or equal to 0?
Yes, that's an equivalent definition. What was the original definition, if you recall? So let's say A is, or let's say sigma. So my claim in this proposition is that a covariance matrix is always positive semi-definite. So sigma is positive semi-definite, sometimes written as PSD, if A transpose sigma A is non-negative for all vectors A in Rn, let's say the dimension. Okay, this is the definition. The eigenvalue characterization is equivalent. So I'm claiming here that the covariance matrix is positive semi-definite. The way I can do it is by a simple argument, and that is to look at the variance A transpose Y for a general vector. So what I'm trying to do here is, let's maybe do it at the end. So what I'm doing is proposition. Let's say covariance of Y is positive semi-definite for any vector, any random vector. Okay, so the proof is I take A in Rn, okay, and then for A transpose Y. So this is like n1 by n matrix vector times n by 1 vector. So the result is 1 by 1, it's a number. Okay, so this is a scalar, so it has a variance. Okay, and I can also write this as the covariance matrix of A transpose Y, because the covariance matrix of A transpose Y is just going to have a single entry. Remember, the covariance matrix has variances on the diagonal and a covariance off diagonal. Because this is a single random variable, there's just one variance. So I can think of this as this is the covariance matrix operator. Now I want to use the lemma tree, which is this formula. So how can I use lemma tree on this? So maybe Jonathan, do you want to call on? We have Avier and Sophia remaining. It would be nice if one of you guys.
I'll call on Sophia, I guess.
Who called on Sophia?
That was me.
Jonathan.
Jonathan, okay. Sophia, do you want to? Is she around? Okay, maybe try Sophia later. Avier, do you want to go?
I wasn't really like following. I was kind of doing the homework on the side, so I'm sorry.
Okay, so now you have to follow that. So let's say covariance. I want to do. Remember, this is covariance of AX, right? This is A covariance of X, A transpose. I want to use this to compute this guy. Can you help with that?
Yeah, should we just take A transpose, so treat A transpose as an A in this case? So we would Right, take it outside. So it's A transpose
Yeah,
covariance
this is
Y.
A transpose, this is going to be A, right?
Yes.
A transpose covariance of Y, A, right? So, okay. This is clear to everyone? This is like A transpose is a matrix. So think of it as this capital A, and then transpose of A transpose is just A. So this is lemma 3 used here. So what do we know about the variance? Can the variance be negative?
No, it
No.
can't.
So this is always non-negative, which shows that this guy is always non-negative, and by definition, this is the definition of the covariance of Y being positive semi-definite. Okay, so it's a one-line proof that shows that covariance matrix is always positive semi-definite. You can see the definition of the positive semi-definiteness is used. And sometimes useful to use it direct. Okay, that's this. There is some sort of idea of when is the covariance matrix positive definite, not just semi-definite, but positive definite, no non-zero eigenvalue. This is this pattern discussion here, which I talk about in the lecture videos. And if you're interested, you can go over that. That's not something that we have to worry too much about. But this is important. Covariance matrices are positive definite, but semi-definite. Okay, is that clear to everyone? Okay. So now we want to do decorrelation or whitening. So this is the last topic they want to do, and then we're going to go move on to multivariate normal distribution. So the idea is that I can use a transformation. Let me do it here. So whitening. So I have, let's say we have X with covariance being sigma. Okay. Can we construct a transformation of X, a linear transformation, such that the resulting vector has uncorrelated components. Okay. So what I want to do is that I want to come up with an A such that if I multiply by X, I get Z, and I want the covariance of Z to be uncorrelated and with unit variance. So I want this to be IN, which is the identity matrix. One's on the diagonal, 0 elsewhere. So the question is, can I come up with a covariance with a matrix A for any vector X such that this holds? And if you, we know, if you expand the first one, we know that the covariance of Z has to be a covariance of X A transpose. And so I want this to be I. And I know that this is sigma, so we need to solve IN equal A sigma A transpose. So I have to solve for A, this equation. So any idea how to solve this matrix equation? So a hint when you're dealing with something like that is to try n equal 1. So you try n equal 1, what would happen? Every matrix has dimension 1.
Would variance just be 1?
So you get this is 1 equal, A is a number, A times, this is going to be the variance. I'm going to call this sigma squared, let's say. And then this is going to be A. Transpose is going to be A. So what will be A in this case? The variance is not 1, but we have A. The variance is whatever the variance is. We can't change the variance of X, but we can change we are trying to make the variance of Z equal to 1. So we have to determine A.
Wouldn't A just be 1 over sigma?
Yes, so I would write it as sigma squared to the negative 1/2. Okay. Does that work? It works. It's like 1 over sigma, as you pointed out. So if you want, I can write it as, yeah, just sigma in this case is sigma squared. So this is our sigma. So what will be the solution of the general one? Can you guess? There's a sigma.
Would it be the matrix, the covariance X matrix squared?
Negative
Should-
squared, right? Something like this.
Oh, yeah.
Minus 1/2. So if you have this, what does this mean? This means that A times A transpose, or basically A times A would be sigma minus 1/2, sigma minus 1/2, sigma minus 1. Or let's say, let's do this. The property, this has the property that it's the inverse of the square root matrix, if you remember. So we can check. I want to check whether A sigma A transpose works as sigma minus 1/2. I write sigma as sigma 1/2 times sigma 1/2. This by definition is sigma, and then A transpose, this matrix is symmetric. You can verify. And so A transpose is itself. So I get this, and then I can combine these two. This would be identity, and this would be identity. So the result is identity. So you can check basically that this works. So how do we compute A equals sigma minus 1/2? How do we compute it? Do you remember how we compute? Or do you remember how we computed the square root matrix? Let's see if I do the spectral decomposition here. Can we compute it based on that?
Yeah. So, Professor?
Yeah.
So the matrix can be written as the spectral decomposition, right?
Yeah, so I can do the spectral decomposition as sigma.
Okay. Then wouldn't we just do the negative 1/2 for the middle, the eigen
Yeah.
part?
Yeah, you can just put the, you can put the 1/2 here. So basically, from this, it follows the sigma minus 1/2, which is our A, is going to be U lambda minus 1/2 U transpose. You can put it on the middle guy. And for this to work, I need the eigenvalues to be strictly positive. So I need to assume that the covariance matrix is strictly positive, no non-zero eigenvalue. But once I have it, I can compute this as if I'm doing it just on this diagonal matrix. So in any case, so there exists this A that we can come up with, which is the inverse of the square root, which can be computed like this if you want, such that when I apply this matrix to X, the result has covariance identity. So this operation of multiplying X by a matrix to make the result be uncorrelated and have unit variance, it's called whitening or decorrelation. It's very similar to the idea of that you use to standardize a single random variable. So for example, if you have a random variable, let's say 0 mean, you divide it by its standard deviation, it will have unit variance. This is exactly that for a vector. So instead of dividing, so you saw that in this case, univariate case, basically transformation is divide like 1 over sigma. So you multiply the scalar by 1 over sigma, which is like standardization, usual standardization. So this decorrelation is like the multivariate version of that. So we can apply this. Not only you standardize the variances, all the variances are now 1, but also make everything uncorrelated. Okay. Does that make sense?
Yeah, Professor.
Yeah.
Just to double check. So we are given a z, or are we given an x that we want to?
No, we are given x. We are given x. What we want to do is come up with A such that the resulting Z has this covariance matrix. Right? That's what we want to do. You're given X, which has this covariance matrix sigma. And you want to construct A such that when you form Z, A times X, then the covariance is identity.
Okay, that makes sense.
Okay, sounds good. So that's basically this slide, if you want. So we have for any vector y, is it possible to find linear transform A such that Z, which is A times Y, has identity covariance matrix? And the answer is yes, and that A should be sigma minus 1/2. Okay, any other questions?
Okay, Professor.
Yeah.
So this is kind of like the spectral decomposition then, because for spectral decomposition, it's symmetrical, or it's like.
No, you can use the spectral decomposition of sigma to compute this matrix.
To compute, right? A. Okay.
Yes, yes, yes. So the spectral decomposition gives you a way to basically solve many problems. In particular, one of the problems you can solve is how to raise a matrix to a fractional power, or inverted, or just integer power. Let's say sigma to the 4. How do I compute sigma to the 4? If you have the spectral decomposition, you just take the diagonal matrix to the 4th power, and then you multiply by u and you transpose. It simplifies, say, for example, computing powers, and it also helps you figure out how to do fractional powers, sigma to the 1/2. You can actually define sigma to the 1/3, for example, similarly, or some like real number, not necessarily rational. But the point of this is not the spectral decomposition. It's just that there exists a matrix that you can construct such that when you multiply out, basically this transformation for any y. If you apply this transformation, which depends on the covariance matrix of y, you get a vector whose covariance is identity. That's the goal of this exercise.
Okay. Okay. Awesome. Thank you. Yeah.
No problem. Any other questions? Was this clear, everyone? This is relatively advanced, I would say. We're not going to use it as often. Lemma 3, and this is good to know. So you learn 3 things. So hopefully at least 3 things, maybe 4. This lemma, which is very useful. How to compute the covariance of a transformation. Sorry, where is it? I've lost. Sorry. Yeah, this formula, covariance of AY is A covariance of YA transpose. You can also use the bilinearity of the covariance operator. That's another thing that hopefully you learn, which comes in handy. the next one is that the covariance matrices are positive semi-definite, which is an application of that lemma basically applied to compute the variance of A transpose Y for a vector A. So this is just a consequence of that lemma tree. And finally, another consequence of that lemma tree is that we can construct a transformation of a random vector such that the resulting random vector has identity covariance matrix. Does that make sense? You can also reverse this transformation. We'll talk maybe about that later. Given Z, which has this simple covariance matrix, I can come up with Y that has a given covariance matrix sigma by just inverting this transformation. So you can verify for yourself that also I have Y is equal to sigma 1/2 times Z. So if I have a Z, if I can form a Z that has uncorrelated entries and diagonal, the variances are 1, and I want to construct a random vector that has covariance sigma, I can just multiply Z by sigma 1/2, and I get that result. We'll talk about this later. This is, for example, how you generate a general multivariate Gaussian distribution on a computer most often. But this is just an aside. Maybe too confusing at this point. Okay, so all this okay, people? Everyone happy? Okay. I'm assuming that you're happy, so if not, please let me know. So now, like, we have about 5 minutes, and I would like to maybe start talking about, so we're done with basic random variables and random matrices. Before we get to the regression, I just want to add one more sorry, I don't have the, I just want to add one more piece to the like background knowledge before we move on to the regression, and that would be sorry, I'll have to put the right. So that's the multivariate normal distribution. Okay, so let's see if this is the right slides. Okay. Okay, yeah, so this is the last topic before we get to the regression. And I want to maybe start by, so the idea is that we want to go to define this so-called multivariate normal distribution. But before doing that, maybe I would ask you guys about the usual, like, univariate normal distribution. So how do you define the usual, like, scalar normal distribution? Oh, Max is widening in lecture 6 video. You have to check. Maybe I have skipped over it. Maybe I'll talk about this at some other later lecture. Just have to check. We're going to talk about something similar at the end of this, let's say, chapter on multivariate normal distribution. Maybe I'll talk about that there, or I'll talk about it where we need it. We just need it at some very specific point in the class, but it's a generally good idea to learn, because it's just a consequence of that lemma tree. We're not going to use it that much. So what is a standard normal distribution, if you recall?
Would you want the the PDF?
Whatever you can give me. So let's say I want to say X, a random variable X. random variable. X has a standard normal distribution. What does that mean?
That means X follows a normal distribution with mean mu and variance sigma squared.
Variance
No.
sigma. So yeah, so this just completes my sentence, but it doesn't tell me what a standard normal distribution is. Yeah, so A has a standard normal distribution with mean mu and variance sigma squared. Thank you for pointing out. Now, what is this? What do we mean by this?
Well, probability of X is 1 over sigma, 2 pi sigma squared times e to the
Say root 2 pi, yeah.
root 2 pi, e to the negative X minus mu over sigma squared over
sigma squared.
2 sigma squared.
Okay,
Yeah.
So this is the formula, but this is the probability or something else. What is this? What
That's
is the name of?
PDF,
Yes.
probability density function.
Yeah, so this is the probability density function, which is not exactly a probability, but it's a probability density function. What does it mean? So it's a density. What does the density mean?
Does it mean that the probability of getting X equals something, or from X equals something to something, then it's the integral of the probability density function evaluated from the two bounds.
Yeah, so basically density means I have to integrate it to get the desired quantity. So the probability density means that if I want the probability to be in a set, I have to integrate this function over that set. Let's say if that set is an interval, it would be like that, but it could be a general set. So I have to integrate. So if you plot this density, you've seen the shape. It's mu, it's going to be some sort of a, has a mode maximum at this, and it just drops down to 0. And so if I want the probability that I'm, let's say, between A and B here, what is the chance that the X is in this interval? I just integrate the integral gives me the area under the curve. So that would be that probability. Okay, so that's the meaning of the PDF. And there's an equivalent way of characterizing things in terms of the CDF, which is just like the function that collects all the probabilities of these half intervals. But this is the way that usually people define. It's equivalent. You can define a distribution of a random variable by equivalently giving the PDF or the CDF. The CDF is a little more general, but for continuous variables, it's equivalent to giving the PDF. So that's how you define a normal distribution. We do the same thing for the multivariate distribution. We give a PDF, but this is now a multivariate function, and you have to take multivariate integrals. And but the idea is the same, and everything goes through. Just the formula is a little bit more complicated. And hopefully next time I'm gonna come back and talk about this. So if you get the chance, go through as much of the multivariate normal distribution as you can over the weekend. I'll try to maybe specify specific portions, but take a look at this, and then hopefully we can come back and talk about the multivariate normal distribution. Sounds good?
Yes.
Okay, great.